Hello, I'm Bill Wong. I'm Senior Content Director with Endeavor's Design and Engineering Group, and I'm also Editor of Electronic Design. And I'm here to help you try to figure out how to generate bug-free software. And let's see if this thing actually cycles. Okay. All right, there we go. Okay, so when we're talking about generating bug-free software, it's obviously going to be coming down to the programmer who's going to be writing the programs. But typically, it's going to be part of a much larger group, oftentimes a team, if you're going to be working in on a particular project or with a company or something like that. And regardless of that, a lot of the software that you're going to be working with is going to be coming from other people. We'll talk a little bit about some general best practices because for a lot of people, that's going to be the best way to improve your software development. And then we'll talk a little bit about some of the tools that are out there, many of which you're obviously familiar with. And then we're going to touch on a couple of programming languages, in particular things like Rust, for example, which is an upcoming language. And it's one that's designed to essentially improve the quality of software by forcing the programmer to be a little bit more rigorous in their definition of the applications. And finally, everybody's been talking about artificial intelligence. It's something that's relatively new from a development perspective, although obviously artificial intelligence tools have been used a lot in terms of generating applications. So we'll be talking a little bit about those things as well. Okay. Now, what I wanted to do is first focus what I'm going to be talking about, because we're not necessarily going to be talking about all software development, although a lot of applications will benefit from a lot of the things that I'm going to be talking about. In particular, I'm looking more at embedded programming, systems programming, things that are going to be a little bit more rigorous. For example, those things that are going to be going into self-driving cars, those things that are going into your routers and so on that need to be secure, going into medical devices where you don't want them to fail. People get rather annoyed at that. So those are the kinds of applications that we're going to be talking about. So a little bit of background on my part, because I've gone through probably a lot of the things that you're going through in terms of learning about applications, making all sorts of mistakes along the way, and thinking, oh, this is a lot of fun. So in particular, way back when, I actually started out with assembly language programming and a programming language called Algol, which was very big on Burroughs Corporation machines, but didn't really make it out into other places. But it was essentially a precursor for things like C, for example. And then basic APL and Forth. Some people may have seen that. As you can see, I have not necessarily started out with the best of things to begin with, but it gave me a variety of things to play with and get some background and make a lot of mistakes along the way. Likewise, in terms of my background, I worked for a company called Rising Star, and we developed something called Valdocs. It was on an Epson QX10, and that was written primarily in assembler and in Forth. Interesting mix. Finally, I worked with Numega Technologies, and I worked on a program called Bounds Checker. And this actually wound up tracking memory and programming interfaces. So it was a lot like a dynamic analysis program that we'll be talking about a little bit later. So lately, I've been playing with languages like PHP, Python, Ada, and Spark, and Rust, two of which I'll wind up talking about a little bit later. Now, one of the things I wanted to do is talk about how my initial mindset was when I started to learn about programming, because when I discovered programming, it was like magic. It's something that I could wind up doing, I could make things happen, and it was all things that I wound up doing myself. Now, if you watch on YouTube, there's a video called the CBC Gathering of Magicians. If you search for that, that's actually about Valdocs. And the interesting thing about that is that the development environment that we had back then was very rudimentary compared to what we have today. There was no autocomplete, there was no IDE, everything was done on the command line. And it was a challenge because effectively all of the quality was in the hands of the programmer. And in general, when you're programming, that's the way you feel. But as you start using more tools that are outside of your actual control, you have to depend upon other people and the quality of that software for your overall solution. Now, as a group, when we were developing ValDocs, we wound up cooperating quite a bit and coordinating, but we also were missing a lot of the other tools that we have now as well. So in terms of bug tracking systems and code logging and so on, those things were all tools that we wound up building ourselves. And unfortunately, when you start building tools yourself and you start developing your background in terms of programming, if you don't necessarily have somebody else that's going to point out details or better ways of doing things, you're going to tend to, sometimes choosing good solutions or good approaches, and other times getting into bad ones. And getting out of the habit of using bad ones can be a challenge. Now, talking now about software that's being developed, we're much better at tracking bugs at this point, and we have a lot of track record in determining what kinds of problems people are going to be running into when they're doing development. Now, the interesting thing is that the C programming language has been very dominant. It still is dominant in the embedded system side of things. But while it turns out to be very easy to learn, it is very easy to make lots of mistakes. And it turns out that MITRE Corporation has been tracking these things, and in cooperation with quite a number of people. The CVEs are essentially notifications of particular kinds of errors, oftentimes in very specific applications. But there are a lot of general problems out there, and the majority of them are memory related. In particular, things like out of bounds checking, going past your array bounds, using null pointers or pointers to data that has already been deallocated. This is especially bad if you're going to be pointing to something that's in the stack, and the data where you were originally pointing to is no longer there. It may be pointing into the middle of some other portion of the application, and that's how you can essentially hack into a lot of systems, is essentially by bypassing what would normally be controls put into place by the programmer to prevent you from causing problems. And of course, it's not just people that are going to be hacking into a system, but it's also just errors that may be occurring where you have corner cases, or oftentimes even complete approaches where you didn't think about how certain things were going to be operating. And in many cases, it's because of tools that you may be using, runtime libraries, for example, that are not operating exactly the way you think they are. So when I was talking before about programmers working on an individual basis, I was talking about essentially programming in the small, as people like to talk about it. And when you're dealing with something like assembler in C, like I was on microcontrollers like a Z80, which was what ValDocs ran on, it was very easy to understand not necessarily all of the pieces, but a large majority of the pieces. Likewise, it was very easy to understand a large portion of what the processor was doing. We literally were able to do debugging because we knew the hex codes for the instructions, and it was just much quicker to wind up using those things and patching directly. Really bad practices, and often you could easily crash systems while you're trying to debug something, but it didn't really matter as much because you weren't affecting as many things. Programming in the large, on the other hand, is what is often terms used with respect to people that are doing development in very big teams. So if, for example, you're going to be doing a self-driving car, there are people that are going to be working on individual ECUs, there are people that are going to be working on the advanced driver assistance, so ADAS. And it's not one person that's going to be looking at all of this stuff. And likewise, there are so many interactive pieces that you typically don't even know what certain other ones are doing. So there are a lot of tools that have been put together for managing big projects like that. The thing is that these days, if somebody, for example, is working on some web pages, What they're depending upon is a lot of software underneath. Oftentimes, for example, I use Drupal. It's a framework. It's a very large framework, and it's being done by a lot of people. Likewise, it's going to be running on top of a web server, which is in turn on top of an operating system. So you have to depend on all those pieces and assume they're all working correctly. Likewise, you typically are going to work with those things from a documentation standpoint, and you have to assume, hopefully, that all of that documentation is correct. Because as a person working on the small portions of the application, if you are making changes and you're not necessarily using that particular tool or runtime library properly, you can easily cause problems inadvertently. So let's back up and talk first about the programmer. You as a programmer, experience helps. You have to understand the problem, you have to figure out how you're going to solve this thing, and then you have to actually translate all of that into programming code that's going to make things work. Now, that means that you have to take advantage of your experience, your understanding of the language and the problem. And usually you construct something that works relatively well. The challenge is that there are lots of details when you're talking about software. Now, if you're using a programming language like C, it is essentially up to the programmer to make sure that all those little details are taken care of. For example, if you have an array, you have to make sure you're not trying to use a pointer that runs off the end or using an array index that goes past it. C will very happily let you do that. And when you're writing your applications, you have to take that into account. Likewise, I had already mentioned that you actually have to understand the libraries and the code bases that you're using. And another piece is that I really didn't put in here is you have to be able to keep track of those things in some fashion because of the way they're being used. If you go back far enough, we were dealing with floppy disks, we were downloading software, but typically you'd wind up working with something that was on your machine that didn't change for a long period of time. On the other hand, now with the internet, you can effectively be pulling directly from repositories that are on the internet that are literally changing as you're potentially using them or changing every night. So what you actually have could be fixing a particular problem related to using that in your application. And the next day, your changes may not work because of changes that happened elsewhere. Now, as you get into larger groups, there are a lot of tools that can be involved, but there's also ways to cooperate with respect to other designers and other programmers. And two of the areas that are often being used are code reviews and even pair programming, where essentially you have an individual and essentially you're doing code reviews when you're designing these systems and actually programming. So you have somebody looking over your shoulder. It's actually very good when you have a more experienced programmer and somebody that's less experienced because they can then teach them and help them learn on what's going on. They oftentimes will spot particular errors that are going on, but they have the same kinds of issues that an individual programmer does. And that is that you can miss these small details. The compiler is typically going to catch something like a misspelling of a word, but if you're going to wind up doing particular assignments, you're taking a different approach to something, those kinds of problems can crop up. And if you don't catch them right away, they can cause all sorts of problems later on. Now, I did mention documentation, and this is actually one of the more important things that essentially anybody that's programming can do, and is also going to be very dependent upon. Now, if you've used a framework like Drupal, if you've used other frameworks out there, they typically are using something like Doxygen, which is based on comments that are put actually inside the code, which in turn is run through yet another filter, and that generates essentially web pages, which are the documentation that is associated with what's going on. What it does is essentially keeps the description of what the code is very close to the code itself, but you also run the issue of how much documentation is going on, how many details, and what you're actually going to be documenting. Oftentimes, these things typically wind up simply telling you what parameters are going to be used, what ranges they may be involved in, what kind of results that may be returned. But it's very basic. It doesn't tell you essentially why you want to use a particular function, what examples would be in there, and things along those lines. Now, what this approach often does help you with is preventing things like undocumented functions and also improper documentation, simply because updating these things now can become second nature. Oftentimes, and a lot of the build systems, you use something like GitHub or other environments. When you upload code, it can often be tested in terms of unit testing and also regenerating documentation. Now, the challenge is when you're dealing with actual development, you have to worry about whether or not those changes are going to be reflected immediately or whether they're going to be approved and so on down the line. But that's a whole lot more in terms of process. Another aspect that is relatively generic in terms of improving the quality of software is using a coding standard. The one I gave here is the bar group embedded C. And essentially, these are generic rules like don't use pointers. There's another coding standard called MISRA. MISRA C is something that was designed for automotive use. And again, it has rules along the lines of don't use pointers, use arrays and indexes because they can be checked. Don't use null pointers, for example. You always want to allocate something immediately if you can. A lot of these coding standards and rules are often dependent upon what programming language you're going to use. So obviously, things like Java aren't necessarily going to have dangling pointers because you can't get rid of data arbitrarily. On the other hand, there are still problems that you can run into. For example, you can have data that is no longer used. It's still out there, but it keeps growing. So you wind up essentially blowing out all your memory, and that can cause problems when programs crash or stop or things like that. So coming up with a good coding standard for whatever language you're going to wind up using is going to be good practice to improve the code that you're going to have. And version management is something you obviously want to be able to backtrack, because creating good code is not just keeping track of all the bugs and fixing them. It's keeping track of how you may have fixed them, because when you wind up coming up with a new bug, you have to figure out whether or not changes that you've made in the past may have caused new problems. And if you're arbitrarily going to be going through and making changes to make things quote unquote work, you may have affected something you tried to fix before. So that's why those things are very important. So we'll get into now some of the actual tools that are involved. I'm not going to talk a whole lot about debuggers because that's a whole separate section, but we're going to be talking a bit about compilers, and obviously because of particular languages we're going to discuss a little bit later, those are going to be very important in how you're going to be able to improve your coding practices to essentially eliminate bugs. We're going to also talk about static analysis and dynamic analysis tools. Now, effectively, a compiler is a static analysis tool. It's going to be doing syntax checking, and from that, once it's gone all the way through that, it actually generates code. The other analysis tools are oftentimes designed to find errors and identify them for you that the compiler itself cannot locate. If you're using something like assembler, or which is not really a compiler, or C, the kinds of things that the compiler or assembler can actually find are very limited because of the flexibility of the language. On the other hand, there are a lot of errors that can be found if you're going to be using a higher level language, everything from C++ to Java and so on. Those kinds of errors can be found at compile time by the compiler. And that's really where you can augment the development that is being done by the programmer. And in some systems, and we'll talk a little bit more about how those are working, they are going to make the job of programming in the large significantly easier. Now, some of the challenges you have along the way when you're starting using static analysis tools. We'll get into those in more depth. But false positives are a challenge there. That's where the tool says, hey, you got an error here. You take a look at the code and go, no, that's not an error. That's what it was intended. And in fact, how it found it may be an accident or an imperfection in the static analysis tool. Dynamic analysis tools actually operate at runtime, and there you have the issue of overhead. It can get excessive. It could literally make an application run 2 to 10 times slower simply because you have more code being executed for the analysis and data capture than you do of the actual application itself. Now, that may not necessarily be an issue. For example, if you're doing microcontroller development and you're working on something that's running at a couple hundred megahertz, and you're actually simulating it and you're running it on a high-end PC or server that's running at gigahertz with multiple cores and so on, you could literally run a program in essentially real time with respect to the microcontroller and simulate it and have that level of overhead. And you may actually want to do something like that, because if you're working on a microcontroller in an ECU for a car that's going to be controlling the braking system, you want to make sure that that thing is going to be working properly. So using that simulation and that dynamic analysis may be well worthwhile. So talk a little bit about the advantages of compilers. Obviously, the tools are all readily available to you. And what they do is they essentially force the programmer to meet language specifications. Now, the specifications for something like Rust, where memory management is significant, those restrictions or the syntax that you're allowed to use and the semantics associated with it are much stricter than something like C, for example, where it's an open ballgame. And essentially, the compiler, through its analysis of the program, can identify bugs that it knows you're not allowed to do. Now, oftentimes, even in Rust, there are exceptions that you would want to have. And oftentimes, programming languages let you essentially bypass some of the checks that the compiler is doing. But you have to do it explicitly, as opposed to writing something in C where you know you're going to bypass it, but you don't really want to bypass that kind of approach on other parts of your code, for example. So again, in terms of the limitations, it's going to be limited by the language itself. Another thing to consider is the stability of the language. And most of those that are being used in general use, especially if you're talking about production compilers, are designed to be at least stable with respect to everybody's general use. In other words, they'll cycle through a major version every 6 months or a year. And likewise, if they are locked down in terms of fixing bugs within the compilers and the tools themselves, those things may be supported for some period of time. Unfortunately, there are also a lot of languages, new languages, Rust is one example, where changes are being made and bugs are being fixed on a rapid basis. Likewise, in terms of open software projects that are out there, oftentimes bugs are being fixed and you'll see a change this week and another change next week, and you sort of have to decide what level you're looking at, because obviously you don't want to have tools that are causing problems because of their errors, or likewise using runtimes that are full of errors as well. Another challenge with compilers in general is where you get them. And we tend to be spoiled at this point because given all the open software and essentially free software that's typically out there, you have to balance that against tools that you're actually going to have to pay for. And some of them can get very expensive. Part of the reason is that level of stability that we're talking about. If you can't trust the tools that you have, how are you going to generate code that's bug-free? Okay, so static analysis tools. Normally what happens is, with the exception of some graphical programming languages like LabVIEW, software is typically written in text mode. And essentially the compiler runs through, does all its checks, and it's then doing essentially a static analysis based on the language. Now, what additional static analysis tools can do is essentially go through that same set of code, but look at it from a different perspective and essentially identify problems that it can find that are not necessarily part of the programming standard, or the programming language standard. And they can also implement checks for things like the bar group embedded C that I mentioned earlier. Those things, for example, like we said before, they would recommend using an array to access things and not using pointers. It can identify the fact that a pointer is defined or how it's used. You could even track, when it's assigned and so on, and effectively identify that as a potential problem. Or if you're essentially using these tools to force certain conditions or requirements on your software, it can essentially say this software shouldn't be compiled and actually run because you are essentially breaking the rules that we've set in place. Now, oftentimes static analysis tools are relatively flexible. You can oftentimes select which rules are going to be associated with it. And likewise, in some cases, you can actually add additional rules. Now, as I was mentioning, rules are typically the way static analysis has been done in the past. That is potentially changing because the artificial intelligence tools, which I'll talk about a little bit later, are oftentimes going to be incorporated into the static analysis tools which are currently available. And all they're doing is changing the kinds of methods that they're using to identify things that should not be happening in a particular program. So instead of having an explicit rule saying, okay, here's a pointer, here's some syntax you shouldn't be using, that it's been trained by looking at good and bad quality software and coming up with its rules. It's a little bit more of a black box and black magic, but that's true of artificial intelligence tools that we know and love today. Now, part of the challenge with static analysis tools is they are still effectively limited by the languages themselves and the tools that you can place or utilize while you're compiling. And likewise, there is additional overhead. Compiling your software takes some time. If running the static analysis tool takes as much time, you effectively doubled the amount of time that you have in terms of that portion of your development cycle. In some instances, it could actually take more time because it's doing a more in-depth analysis. And a lot of these tools can often be tweaked one way or another such that the tool becomes more effective, but taking more time. And then, as I mentioned before, false positives, and that's where here's an error that really is an error. Likewise, there's false negatives where it completely misses something that you thought it was going to be catching. Okay. Dynamic analysis tools are typically incorporated either by explicitly including additional code into your source code, or jumping in at link time, or jumping in at runtime, and essentially inserting additional code into the program itself. And what it will often do is check, for example, function entry points. That's what Bounds Checker did. It actually took a look at the various system calls and essentially patched in so that every system call was tracked. And trace tools work in this same fashion. The difference between trace tools and dynamic analysis tools is trace tools simply do a recording. Dynamic analysis tools, on the other hand, are actually analyzing what's happening and essentially trying to catch errors. For example, if you're calling a function and it's supposed to point to an array and you give it a null pointer, it should execute the function. Now, the function itself may have been designed such that it checks for that, but in many cases, you can't depend upon that. And likewise, the code that you're going to be using may have been designed explicitly so that wouldn't be the case. So you have to figure out whether or not these dynamic analysis tools are going to be able to improve and catch those kinds of errors along the way. The runtime overhead, as I mentioned before, can be significant. Now, dynamic analysis tools that are running in the system and doing the checks in the code can often have less overhead than ones that are going to be shipping data out to a trace facility or something like that, because they can essentially catch or determine that there's no error very quickly. For example, when you're checking for a null pointer, that's just a very easy check that's going to be in there. Very minimal overhead. But if you actually have to, for example, get a pointer to a file descriptor and you want to make sure that the file is open, that's going to take additional code that you're going to have to be running. Okay. There are additional pieces that are potentially working in this fashion. For example, there is a technique called fuzzing. And this is where essentially you wind up throwing lots of test cases to an application, taking a look at how it responds, and trying to catch corner cases based upon this. Fuzzing is a technique that can be used at the function level. It can be used all the way up at the application level. I'm not going to dive into a lot of these things in detail. Some of them may be obvious that you've used before, and some of them may be relatively new. There's another one out there from BG Networks called Answer. This is a tool that actually takes a look at your application, and it uses artificial intelligence to essentially take a look at various hooks. So it's essentially doing some dynamic analysis and taking a look at the set of functions that are being used, say, for example, talking to the operating system, and learning which functions are significant based upon overall operation of your application. And then identifying what should be a good execution of a program and trying to be able to essentially mark when something is going off into Never Never Land. Take a look at it. It's much more difficult to describe than I'm going through here, but it's potentially a very interesting tool. I did mention unit testing, and this, in terms of generating good code, is probably one of the easiest things to do. It's also one of the most annoying things, but effectively, unit testing is where you write a particular function. You write another function which essentially checks that. Given certain inputs, calling the function, getting certain outputs, the unit test function says, okay, here's the data going in, here's the data going out, and it's valid. And there are a variety of ways of implementing these things. The advantage is if you are making changes to the underlying code, especially if you're going to be doing something like using somebody's runtime, making sure that those unit tests that you are associating with that software means that that code is, in theory, not going to be changing underneath you and causing additional problems. And essentially, the unit testing that might be occurring at the application level is often talked about as quality assurance or the QA group and regression testing. So, and finally, I wanted to mention model-based design. This is essentially a different programming methodology that I didn't want to get into, but especially when we're talking about applications that require safety or security concerns, oftentimes there's a high-level model or description of what the application is going to be, the restrictions that might be placed on it, the kinds of checks that it's going to be doing. And that in turn is something that a programmer then has to take and convert into an application using something like C, C++, or Java, and so on. There are also tools out there where the model itself can literally generate the actual source code. And that in turn can be compiled and generated. There are graphical programming languages that are effectively model-based designs like LabVIEW. And while LabVIEW can generate applications directly, it can also, with the appropriate tools, generate C, C++, Java code, which in turn could be incorporated into another application. So if you're developing part of your application in LabVIEW, you can then take that piece out and wind up making use of it elsewhere. Okay. So now we're going to get down a little bit more into the discussion of some of the languages, some of the challenges that are going on, and potentially some of the solutions that may help improve things. Now, the biggest challenge right now is if you're using one of these languages, switching over to something else could potentially be difficult. Likewise, if you are in an environment where you can essentially mix and match programming languages, you can essentially take that approach and maybe utilize one of the other languages in an area where you're developing new software or in software that may be more dependent upon, or not dependent upon, but require a higher level of quality. Some examples that I've written about recently: the security processor for, I think it was AMD, was the software that actually runs on that security processor was developed using Spark, which is a variation of Ada, which I'll get a little bit into a little bit later. Likewise, in terms of device drivers for the Linux kernel, the Rust language has now been, quote unquote, okayed to be used. Prior to this, everything was being written in C. Now it's possible to essentially use Rust. So if you're running on a system, you may actually be running some Rust code, and the rest is going to be written in C. But it's essentially in a cooperative environment. So the other thing that I was looking at was, in terms of the languages that I'm mentioning here, all of them are compiled. They're all suitable for what I call bare metal applications or operation. And this means if you're going to run on something like a microcontroller where there's a limited amount of memory, you don't want to put an operating system, or maybe you're writing your own, that these kinds of tools can be used to target those platforms. Likewise, they're all, with the exception of Rust, which is going to be changing in the near future, are suitable for safety and security certifications. The rigor that is required for that is not just in the tools or in using a particular language. There's typically a whole lot of other paperwork and procedures and whatnot associated with it, but you can't do those alone. You have to actually have the compilers and everything certified as well. So these all fall into the category where you can get those kinds of tools and make those kinds of applications. So we'll start out with C. This is what the majority of people are using because A, it's free. B, if you take a look at any of the microcontrollers, microprocessors, whatever that are going out, they will have a C compiler for them, bar none. And likewise, all the runtime support's going to be in C, and a lot of the third-party tools that you may be using are going to be in C. So that's why it's very popular, and obviously it's a pro for using it. The problem is that C is a very error-prone language. There are all sorts of problems here that we have listed. The fact that you can't hook in any kind of runtime checking tends to be an issue. It makes it much more difficult as a programmer to try to improve your quality of code, short of improving your experience and potentially using some other tools. And that's why I mentioned using third-party tools here, because if you can use static analysis tools, you're going to stand a much better chance of generating bug-free code than you will if you just use the C programming language alone. Now, a lot of the compilers are doing static analysis, and there are certain flags, for example, that you can turn on that will do additional checking in terms of pointer assignments and things of that nature. Turn those things on. Those are going to be very important in terms of trying to catch those little details that you tend to overlook. And in general, you want to use other software to make sure that your software has as few bugs as possible. And these are the ways that we're going to see how other languages are going to wind up improving things. So C++ is one that a lot of people look at. It's a higher level language. It has things like object-oriented programming. But in terms of developing bug-free software, some of the tools that are made possible by things like object-oriented programming, in particular, smart pointers, make a considerable difference in terms of the problems that you're going to be running into in terms of applications. Same kind of thing like containers. Instead of using just a straight C array and pointing to it with a dumb pointer, You can essentially use containers that will limit the access to the data while still providing flexibility. For example, you can have static size containers that don't enlarge. You can have ones that dynamically grow and shrink. All of those things are written in such a fashion that from the person that's going to be using them, you're going to be able to essentially ignore the kinds of problems that you would have had if you used C explicitly. Challenge is that you actually have to use them. Likewise, the type system is going to be significantly better in terms of forcing the match between the various pieces that you're going to be using in terms of assigning pointers, for example. Now, there are some cons to using C++. It still has what I call C-style data limitations. Essentially, you have bytes, words, things of that nature. And you don't necessarily have additional checks to see whether computations are going to go out of bounds. For smart pointers and smart containers, you can essentially check your bounds, but if the pointer values that you're calculating are incorrect, you're essentially going to wind up with additional bugs in your software. A typical problem is you're using a byte to store something, and all of a sudden you have a value that's 1,000. It's going to wrap around, and it could be a very difficult problem to find. Likewise, because of the tests you may have been doing or testing for, you may not actually find that because it's a corner case that you have decided isn't important. So if you're trying to use 1, 2, 3 as your test cases, think of 1,000, 2,000, and 10,000 along the way as well, because those are going to potentially hit corner cases that you're not going to find otherwise. Now, one of the challenges for this language and the other ones is that they tend to be much more complex, and using certain features like generics and so on are going to require a better understanding of the language. C also has the C macro problem, which I'm not going to get into, but C's macros tend to be useful, but they can also cause you tremendous problems and errors along the way. So now I'm going to move and talk a little bit more about Rust. The challenge with Rust is that if you're going to be programming in C, moving over to Rust is going to be quite a bit different. It uses a different syntax, so going from C to C++ is relatively straightforward, using the same syntax and so on. Moving over to Rust, on the other hand, function definitions completely different. Assignments look the same, but they're not necessarily going to be operating the same. Now, in particular, one of the things that Rust is designed to do is identify those kinds of problems that are generally found in applications and forcing the programmer into sort of best practices. So, for example, it essentially has what is called a it's doing memory checking. Oh, excuse me. It's called a borrow checker. The idea being that in Rust, you can use pointers, but with the pointer, only one person or one variable within the entire program should be pointing at the data in a fashion that you can actually make changes to it. Whereas if it's going to be passed as a parameter to some other function, you have the choice of moving who owns things depending upon how you're writing the program. The other thing is you can essentially say, okay, I'm going to give you a copy of this pointer, but you can only do certain things with it. Or likewise, it's only going to last for a certain period of time. And what it prevents is a lot of the errors that would be in C. For example, you point to data that's essentially allocated in the stack, which is some local arguments. Rust will not let you return that pointer back from the function because it's already checking to make sure who has control over things. Another challenge with Rust is it takes a different approach to polymorphism. It doesn't have object-oriented programming, classes, and things like that. But it does have the ability to say, okay, here is some data over here, and this is going to be squirrel, okay? And here's another thing over here, and it's going to be a cow. And we're going to make them both animals, and animals can do certain things. It actually works a lot like interfaces in other programming language, where essentially you define the functions that can be applied to these things, but not necessarily what the data actually looks like. The class system in C++ and in Java, for example, typically meld the description of the functions with the actual implementation. Now, you can essentially get virtual systems that you're only defining the set of functions, but it is a subset as opposed to the superset. In the case of Rust, that's all you get access to. Let's see. Now, some of the challenges with Rust is that it's evolving. It's a relatively new language. If you take a look at most of the other ones that I've been talking about, they're literally decades old. Now, they've been evolving over time, but they also have this stable platform on which they people can develop software, and they can count on the tools being stable as well. There is a company called Ferris Systems, and they're working on a version called Ferrocene, which is being done in conjunction with a company called Adacore, both of which are involved in doing tools which are designed for high security, high safety applications. So we will probably be seeing a version of Rust that falls into that category within the next year or so. Part of the issue is that the changes to Rust are improving as it's going along the way. There are obviously little bug fixes that are going along the way as well, but that can be a challenge. If you're looking at improving your code quality, even if you don't use Rust, look at what it's doing. Look at how the programs are being written, even potentially write a program in it, and you can then translate it over to C. You stand a much better chance of making sure that that program is going to work properly and not have these kinds of common errors that everybody tends to be running into. The other one that I'm going to talk about, and I'll be ending relatively quickly with this, is Ada and Spark. Now, there are a lot of myths about Ada and Spark. If you go on electronic design, you'll find 11 myths about Ada. It has not gone away, but it is not very popular. I wish it was. And part of the reason is that it winds up doing things that most other programming languages don't. For example, if you're going to be defining a variable, you could literally say that it's going to be 5 bytes or 5 bits long, and it's going to have a value between 1 and 6. Okay? Why do you want something like that? Well, if you're going to be passing data, using data defined like this and passing it into a function, the compiler can actually check to make sure that you don't assign any data to that that doesn't fit within the range. Which means that when you finally get over to the function that you're calling, you don't have to check that. You can even do it in terms of types. Now, one of the things that Ada added to its bailiwick is something called contracts. Now, when you're programming in other languages like C, you have something called an assert, which is really essentially a macro that says, here's an equation, and if that equation is true, then we're good. If it's not, we're going to cause a particular error in the compiler and saying, hey, something's wrong here. The challenge is that that requires you to essentially deal with equations that are going to be dealing with constants. And it's essentially evaluating within the environment that you're compiling in, the program's written in. Contracts, on the other hand, are essentially programs within programs. You can sort of look at like unit tests, except for the fact that the unit test is part of the application itself. So what a contract looks like in Ada is there's the function definition, then there's the contract saying, okay, here's what's going to happen, and then you actually have the execution of the code. It can essentially check all the parameters that are coming in. It can check the data that's going to be returned. And it can do this at a static level, which means that when you compile the program, you're going to be able to find these errors. Now, if you're really paranoid, you can turn it on so that some of these checks are actually done at runtime. And that tends to be useful in testing systems where you want to make sure that what you told it to do is what it's going to do, and that there are no exceptions because of other hardware changes and things like that. Now, what these contracts allow you to do is significantly more analysis as to how these functions are going to be related. Because if you put a dependency on the parameter that's coming in, the functions that you're calling can also take a look at that. And if there are contracts associated with the functions you're calling, that restriction can be rippled through the entire system. Now, if you essentially are using a runtime or middleware that's defined and you have access to all the entry contracts that are associated with that, the software that you're writing can now depend upon that. What Spark is essentially will allow you to use those contracts and prove that the program is doing exactly what you specified. Now, the other advantage is if you've proven that the program is going to work properly based upon those specifications, you could effectively remove any checks that are going on. Now, if you wrote a default Ada program and you had an array, it's going to, by default, do a bounds check on every access into the array. However, if it knows, because of the definitions, and you're going to be essentially forcing the additional checking going on at compile time, you could effectively get rid of that additional bounds check. And it could even be more sophisticated than just saying, okay, I'm using constants. It can take a look at the actual code, make sure if you're going through a loop that if you give it a starting point value here and have an ending point value here, and it's going to be incrementing along the way, and I can't change the actual data any place other than this, I can guarantee that those values are always going to be within the range of the array, and I don't have to do any checking. So it winds up forcing the programmer to be more rigorous in terms of the way they write programs, because the compiler is actually forcing that restriction on you. Now, there's an interesting saying is, it's very hard to write programs in Ada, but if you get it to compile, it's going to run. That's sort of the flip side of a lot of other languages where, okay, I can get it to run, but God, there's a bug here someplace and I have to find it. So likewise, in terms of mixing languages, Ada and C have been coexisting for a very long time. Spark lets you essentially prove what's going on. You'll find a lot of cross-pollination going on. For example, there's a system in Rust that is called crates, and that's how they manage their applications. Ada and Spark have picked that up, so now you use crates to create Ada and Spark applications. It's more terminology than anything else, but the approach is essentially the same. Okay, I don't have too much time because I have to wrap this up, but I will essentially want to talk about artificial intelligence. It's obviously been used in runtime applications and middleware where you're trying to use it to identify things so that your application can be more sophisticated. The use of it within checking, the BG Network's answer, for example, is using artificial intelligence to check your software. Right now, there are things like ChatGPT where you can ask it to actually look at your software and improve it, or potentially write something. While that is possible, people are doing it, I would not recommend it in general, other than to say, okay, here's something that I could start from and start working from. You're not going to get safe and secure code from ChatGPT right now. Okay, but that's not to say that these approaches aren't going to be working in the future. Likewise, there's a piece of software called Copilot, which I think is on GitHub. And effectively what it does is when you check in your code, it's actually going through and checking your code to see what things shouldn't be done. And again, general recommendations as to what's happening. And those can potentially be good. The biggest question on a lot of these tools is what the level of false positives are, because if you wind up using it and you spend more time checking for things that it's checking or telling you about, it's not necessarily going to be a useful tool. So you're going to have to look at these things to try to figure out whether or not any of them are going to be useful. We do know, for example, the other static analysis and dynamic analysis tools that are out there that are commercially available are effective. The challenge is they tend to cost money. There are fewer and less quality open source tools out there. That's one reason why using tools at the compiler level tend to be a little bit better, because those are generally available at this point. For example, Ada and Spark is available on as open source, and so is Rust. So with that, I've actually probably run over time just a little bit, and I can probably take maybe one question if there is any of them floating out there, but anybody have anything? Okay, everybody.
Wait.
Oh, okay. Go ahead.
GPT-4 that just got released this week.
Yes.
So any assessment of it yet or anything?
No, I haven't been able to play with it yet. And I would say in general, with all these tools and with AI in general, they're always improving. And it's improving from two standpoints. One is the quality, which is actually more important. The other is the speed. And it's kind of interesting because literally you're seeing orders of magnitude improvement in terms of performance on these things, simply because the approaches they've been taking have either been limited by the other underlying software and hardware, or even just the approaches that they've been doing, because they simply have not been trying to optimize it appropriately. But again, the biggest problem is, you know, what are you going to wind up getting out of this? Playing with small tests that a lot of these things are using right now. Give me a small program, 10 lines, 100 lines. That's going to be easy to check. Give me a 10,000 line program that's going to handle my braking system? No. Okay. And likewise, what I do find them much more useful for is what they're targeting them for, and that is for searching out and finding what's good. For example, searching on GitHub, find me 2 projects that are going to be handling a serial port of doing a particular function. And the description of that function is more complex than just, you know, straight serial port. It's going to be able to potentially narrow down the focus of what's going there. If it does miss something, okay, that's not too bad, as long as it finds me something. But then I have to take that and figure out what's going on. It doesn't tell me whether I can improve the quality of my software by doing that, because essentially I have to then check that software. You could use ChatGPT and say, okay, look at the software now and say, you know, how good is it? Is there errors in it? You know, or how should I modify it? That's always the biggest challenge when you start working with systems and modifying it. It's also one of the things you want to look into in terms of Rust and Ada. Both of them are designed to make it much easier to take other code and make sure when you use it and you've either modified it or incorporated it in your software, that it's going to work the way that you think it's going to work. That's the biggest problem with using C and C++, and even some other languages like Java. If you try to take that piece and you try to modify it, the documentation, the intent, the tricks that may be used, the implications that you have when you were actually, or somebody was actually coding that, may be different than what you have. And that's where those problems tend to creep in. You know, most of the bugs are not out there because people have made, you know, glaring mistakes. They're because I did a typo someplace and I'm adding something or incrementing something. I'm doing an assignment over here and I assigned this variable, which is going to go in the stack and it's going to go away when the function goes away, as opposed to the allocated one over here where I really could have done it. And those little types of changes aren't necessarily going to be caught by the compilers unless you have one that's forcing you to do those explicit kinds of definitions. And Rust and Ada both do that. So, you know, if you are going to be writing a security system and it's going to be self-contained, I'd write it in Spark. You know, if you're going to be doing a device driver and you're going to be putting it onto Linux, I'd be doing it in Rust now. Okay. Those are smaller pieces. The bigger challenge is for those people that are writing other environments as to how you're going to incorporate any of these things and whether you're going to be dependent upon other third-party pieces as well. So for example, you know, you may have a bunch of legacy code that you've written. You're going to be writing some new stuff, and you could take one of these other approaches, but you're also using third-party tools, third-party runtimes, protocol stacks, things of that nature, which are completely outside your purview. The best you can do is say that the stuff that I'm writing is going to be free of bugs. You can't guarantee that somebody else's stuff is going to be there. So, you know, make sure when you're choosing things and where you're getting them from and how you're downloading them and incorporating them into your system are a way that you can trace and keep track of them, which means using those other tools that we talked about briefly, and potentially using other things like unit testing, where you're going to be incorporating the actual testing of those other pieces underneath you to make sure that you have not induced any errors into what you're doing. And likewise, that what you're getting back from them is going to be utilized properly. So if you're, for example, getting pointers back, you're doing checks to make sure that things are valid. Things that you may not necessarily do if you could assume that the runtimes are actually working the way they're supposed to. So any other questions? Great. Okay, well, thank you very much.
Yay.